Okay. All right. Back to regularly scheduled programming here. Okay. So, again, just to kind of summarize, we're talking about these acid base titrations. Okay. Again, we have our analyte in our flask and our titrant in our burette. All right, and this acid-base titration, we're going to be adding that titrant into our analyte. We get this pink color that forms, and then we would stop our titration once that pink color persisted. However, in this course, we have a different goal, which is to calculate the pH at each point in our titration. All right, what is that pH change after each drop of that base? Cool. All right, so where we're going to start is with that strong acid, strong base titration. Okay. Let me just get rid of this real quick. So this was that curve that we were looking at. Again, we said that that middle region, that equivalence point, this is going to be a very important definition to keep in mind in this chapter. This is when the moles of acid equal the number of moles of base. Okay, and we're going to break this titration region up into these different curves, and the very first one is just that very first data point before any base has been added. All right, so we're going to call these in our strong acid, strong base titration our different titration regions. All right. And in titration region 1, we simply have a solution of strong acid. Cool. So then let's do our region 1 calculation. Or rather, get an example here. All right, and again, we have a solution of HBr with a concentration of 0.50 molar. All right, so how are we going to go about calculating our pH? Negative log of that concentration, right? We calculate our pH just like we know how to do for a strong acid. Because importantly, the concentration of that HBr is equal to the concentration of hydronium in that solution. Right? So I know that my hydronium concentration is that 0.5 molar. So my pH, I'm just going to take the negative log. That's 0.50. And I get 0.30102999. All right, and this is really the only point in our titration curve that we can do this. If we have like an ice table, I tell you how many decimal places, but this is just a very simple calculation here. So we have to know that our 2 sig figs will correspond to 2 decimal places in our pH space. So my pH of my initial solution is 0.30, no units. Cool. All right, so that's how we deal with that very first point along our titration curve. We haven't even started our titration yet. So now let's look here. Now we want to deal with this middle region right here. After that very first data point, but before we've reached our equivalence point. All right, when we're starting out with our flask, it's just acid, 100% acid in there at that first data point there. If we're before the equivalence point, that point when the moles of acid equal moles of base, what do we have more of down here, acid or base in the flask? Acid, right? So first of all, that checks out because I'm at this nice low pH, but also, again, I haven't reached my equivalence point yet. So I have less base than acid in our flask. So this second region of our titration curve, this is when we have an excess of strong acid. All right, so let's get an example of a problem from this region here. This is our titration region 2. All right, so we're going to take 500 milliliters of that 0.50 molar HBr solution, and we're going to titrate it with 20 mLs of 5.0 molar NaOH. All right, what is the pH? All right, so first of all, the sodium, what is that doing for me? Nothing. All right, so let's just get rid of that, replace it with the minus sign so we get our actual base here, the hydroxide ion. Now, I've combined an acid and a base together at this point. Okay, so in order to figure out my pH, I first need to figure out how much of this acid-base reaction has occurred. All right, this is exactly what we learned how to do last unit. Our acid-base reactions. Everybody take a second. Just give me that chemical equation. All right, I have my HBr reacting with that hydroxide to produce my conjugate base, bromide, and water. All right, and how are we going to figure out how much of this reaction has occurred? An ice table. All All right, but here's the catch. Here's where it's going to get a little bit different than what we did previously. And it's literally the only difference. So as long as we can wrap our head around this one small change, we're good to go. This is the same thing we learned how to do previously, okay? The big difference here is by virtue of how a titration works, we're changing the volume of this flask as we go through our titration. We're constantly adding volume to it. So we can't do our ice tables in terms of concentration because our concentrations are always changing. Concentration is moles per liter. If the liter part is changing, your concentration is changing. So when we do our ice table in a titration, we have to do our ice table. We got to go back to that more fundamental unit. You know, bottom line is basically we've been being kind of lazy here by doing ice tables in concentration. It's worked out for us because our volumes have been constant. But really, we need to go to that fundamental unit that we use to keep track of chemical reactions, moles, right? That's how we keep track of how much HBr is consumed and all that jazz. So our ice table here has to be in moles, or in this case, it's going to be more convenient to use millimoles. So when I do my ice table, I'm not going to do bracket HBr. I'm going to do millimoles HBr and millimoles hydroxide being converted into millimoles of bromide and millimoles of water. All right, so let's do our first box together, and then I think you can take it away from there. All right, so we've done these kind of conversions a whole bunch in labs, so let's just remind us how we go about converting to millimoles here. I'm going to need to use my volume, my 500 milliliters of my HBr, and my concentration in order to convert to millimoles. All right, so my calculation here, I'm going to take my 500 milliliters and I'm going to multiply it by that concentration, 0.50 moles per liter. The liter part cancels out, leaving me with units of milli and mole. All right, so I am going to start this reaction with 250 millimoles of HBr, of hydrobromic acid. All right, now since we started out with 20 mils of the 5 molar hydroxide, everybody take a second and fill in. Actually, we can do the rest of this row here, right? We don't have any products. These ones are easy. But fill out that hydroxide box for me, and then fill out the rest of our ice table just like we always do. All right, millimoles of hydroxide. We're going to take that 20 milliliters and multiply it by our 5 moles per liter. The liters cancel, leaving us with millimoles. In fact, 100 millimoles. My change box, we're going to use that variable. Our reactants decrease and our products increase. So summing that all together, we get 250 minus x, 100 minus x, x, and x. All right, so then if we just want to put in a solution row here as well, how are we going to solve our ice table? Do we have a Ka for this reaction? No, this is not an acid dissociation reaction. This is a reaction where actually both things are strong. So we have our all strong reacts principle. So then I'm going to be left with no HBr or OH at the end here. Exactly, right? And that doesn't make any sense. You can't pick a value for x that's going to turn those both into 0. All right? We got to be careful. One of these reactants is going to be consumed first. In this case, our limiting reactant is that hydroxide, which checks out because we said in this region of our titration, we should have an excess of our strong acid here. So we have 0 of that base left over, but 150 millimoles of HBr. And we made 100 millimoles of bromide and 100 millimoles of water in this reaction. So now we just got to do our last step here. We have our ice table. Let's calculate our pH. I am left with a solution that's a mixture of my HBr, bromide ions, and water. I don't have any more hydroxide left over. All right, but not only do I not have any hydroxide, there's a few other things on this table I don't care about. What do I get to ignore? I get to ignore water and the bromide. We get to ignore our neutral products. All right, ignore the things that are neutral. So what I'm left with is simply just a solution of strong acid HBr. And so I can calculate my pH the same way I do for other solutions. There's just one catch here. All right, because we converted to moles in order to do our ice table correctly, now we're going to have to convert back to molarity. Right? Our pH is the concentration of hydronium ions, so I need my concentration of HBr. Excuse me. Thank you. All right. Concentration, molarity is what over what? Moles over liters. So what I know is I have my 150 millimoles of HBr. That's what my ice table told me. If I can divide that by milliliters of solution, that milli cancels out, leaving me with moles over liters or molarity. All right, going back to our problem and reading carefully here. What is the volume of our solution? All right, we started out with 500 milliliters in that flask. All right, but then we added a whole bunch of titrant to it. We added a volume of 20 milliliters. So our new volume is the 500 we started with plus the 20 that we added. All right, so I'm going to just write this out the long way here. Our initial plus the titrant added will give us our total volume. Okay, so punch that into our calculator. Our HBr concentration has now decreased, right? It started out at 0.5. It's now 0.28846. Just copy a bunch of digits down. Molar. So if I know my concentration of HBr, how am I going to get the pH? Negative log, because it's a strong acid, right? So I can just do the negative log of that concentration. Or a pH. We're now just going to tell you 2 decimal places, 0.54. Okay, so this is exactly this acid-base reaction problem that we learned how to do last, I don't even know, 2 weeks ago. All right, the only difference is that instead of just giving you concentrations, we're making it more practical, right? I can't take a solution that's 0.5 molar hydrobromic acid and snap my fingers and magically make it into a certain concentration of hydroxide. You have to add volume to do it. You have to mix these solutions together. So these titration problems are going to have us keeping track of that change in volume. We're going to have to use an ice table in moles. And then when we get to the calculate our pH step, we're going to have to convert back to molarity. All right, that's the only difference between what we learned how to do previously and these titration problems. I'm going to gloss over that third titration region for right now. All right, that third titration region is our equivalence point. Whoops, where's ours? There we go. All right, and let's instead look after our equivalence point. Right, at this region here. If I'm past my equivalence point, I got to the point where there is the equal number of acid and base, and I just kept on adding more and more and more base, what am I going to have more of in my flask now, the acid or the base? The base, right? So at this point here, in our titration region 4, now we have an excess of our strong base. And this calculation is very, very similar to what we just did, so I want to see if you guys can do it from the ground up here. We're going to keep our same initial solution, our same analyte, that 500 milliliters of our hydrobromic acid. Okay, but now we're going to have added in a total volume of 70 milliliters of that 5 molar hydroxide. So now this is for our titration region 4. All right, I'm going to update this problem and now say we're going to add 70 milliliters. Our chemical reaction is the same. We again are going to need to fill out an ice table in moles. All right, so everybody take a second. I'm going to give you a bit of a head start here. See if you can't tell me the pH in this region 4 of our titration curve. All right, so we still have that 250 millimoles of our strong acid that we start out with. Whoops, not 50. All right, but now when we calculate how much base has been added, we have 350 millimoles of that hydroxide. All right, no bromide or water. Okay, we do our change box. Our reactants decrease. Our products increase. Sum them all together. All right, so previously we had set that hydroxide box to 0. Are we going to do that again this time? No, why not? Because we're limited instead by that amount of strong acid. All right, so that's what's going to be consumed. So that X value must be 250. So that means I'm left with an excess of that strong base, as well as 250 millimoles of bromide and 250 millimoles of water that we made. Okay, when we go to calculate our pH, we again get to ignore the neutrals. I get to ignore the HBr because it's not there. I get to ignore the bromide and the water because they're neutral. Again, the only difference here is that now we have to convert back to our molarity. So I want the concentration of hydroxide. That 100 millimoles divided by my total volume in milliliters. What is my volume of my solution at this point? All right, so I have my initial volume of 500, and now I've added a total of 70 milliliters of that strong base. So yes, I'm going to take my 500, and I'm going to add that 70 mils. And I get 0.175438 molar. Cool, so I'm going to take the negative log 0.7558, and I'm done. If I take the negative log, what did that give me? The pH? pOH, right? Because what I have when I have an excess of base is that hydroxide concentration. So if I want the pH, I'm going to have to take 14 minus that value. We're going to just put 2 decimal places on there, 13.24. All right, so these titration problems, kind of a good news thing if you understood our acids and bases reactions that we were talking about last unit, because it is incredibly, incredibly similar to that process. It's just now we've had this added little difficulty of not just sort of mixing 2 solutions given their concentration, but a much more practical sort of what volume are we using to mix together, right? And because of that practicality of changing that volume, we have to do our ICE table in moles or millimoles, and we have to calculate, when we calculate our pH, we have to convert back to molarity. All right, so we skipped over one here, our equivalence point of our titration, right? When moles of acid equal moles of base. All right, so this is our titration region 3, our equivalence point. All right, and again, very important to remember what it means to be the equivalence point. All right, that means that the moles of acid that you started out with initially equal the moles of base that have been added. Okay, so let's think about calculating the pH at the equivalence point. I'm going to do it the long way here, and then show you guys that we really do not have to do it the long way at all. All right, we're going to take our same chemical equation. We're going to build an ice table here. All right. Starting out with this same solution we've done throughout our problems today, we've already established that we initially have 250 millimoles of HBr in that flask, right, our analyte. So if I'm at the equivalence point, how many millimoles of hydroxide do I have in that flask as well? These have to be equal to one another at the equivalence point. So this is also 250 millimoles. Don't have any bromide or any water. Our reactants decrease, our products increase. All right, so when we sum these up, we get 250 minus x, 250 minus x, x and x. All right, well, in this case, what's my limiting reactant? Both of them, right? They're present in that, just by the definition of the equivalence point, they're present in the exact same quantities. So that means none of my strong acid or my strong base will be left over. Right, my x value here is that 250. Okay, so if we move on to calculate our pH, what do we have left in our solution at this point in our titration? Only the neutrals. Right? I don't have any strong acid. I don't have any strong base. So absolutely, the only thing left over are these neutral conjugates here. So what's the pH of this solution going to be? Whoa, 7. All right, so calculate the pH. And we just want to make note here, for a strong acid, strong base, the pH is always 7 at the equivalence point. All right, so doing an ice table here was completely overkill. Okay, it's always going to be that value of 7 because what we're left with is just those two neutral products, right? By definition, I have exactly as much acid and base in the flask, so none of that is going to be left over. I only have my two neutral products. Okay, one a little bit more tricky thing, so that's the easiest thing I could ask you. What's the pH at the equivalence point of a strong acid, strong base titration? Always going to be 7. A little bit more complicated here would be how much of that 5.0 molar hydroxide was added to reach the equivalence point? By how much? I can even be more specific. What volume? Was added to reach that equivalence point? All right, and the most important thing here is our definition of our equivalence point, that moles of acid, whoops, that we started out with initially, equal the moles of base added. Or in this case, because it was more convenient, we want to use millimoles of acid equal millimoles of base added. All right, well, how many millimoles of acid have we been starting our titration with? At 250. So that means we have 250 millimoles of hydroxide at the equivalence point. All right, so take a minute. Given our moles, millimoles, and our concentration, see if you can't tell me how many milliliters we needed in order to get there. All right, so we need to take that 250 millimoles of hydroxide, and we know that there are 5.0 moles in 1 liter. So if we divide by that concentration, we'll see that the moles cancel out, but the milli does not, leaving me in units of milliliters. All right, so punch that into our calculator. We get 50 milliliters. Again, this is the volume of 5 molar hydroxide required to reach that equivalence point. Okay, so at our equivalence point, importantly, if I ask you for the pH at the equivalence point, that's an easy one. It's always going to be 7, because the only thing that we have is our neutral products left in solution. all that strong acid and strong base has been consumed. But I could also ask you what volume it took to reach the equivalence point. You got to go back to our definition of what it means to be at the equivalence point. We always know how much of that analyte we start with, so we just set that equal to the number of millimoles of base added. All right, in this case, we're going to divide by our concentration, so that moles cancel out, leaving us with volume units of milliliters. Cool. All right, so just to review here, we're talking about these acid-base titrations, all right? But we have a very different goal than what we've looked at before when we were doing titrations. Normally, we only cared about the endpoint, right? When we do our analysis for this green salts lab, we're not worried about every point along that titration. We only care about the endpoint, and then we do some stoichiometry with it. In this chapter, though, we're worried about calculating the pH at each point along the way in our titration. Okay, and so what we started out with today is a strong acid, strong base titration. So our analyte in our flask is that strong acid. We're going to titrate in that strong base, and we get a curve that looks something like this, right? Our pH starts out really low. It starts to increase as we add base very slowly, and then it shoots up through this vertical region here. That midpoint of that vertical region is our equivalence point. You can see it's at a pH of 7 right here. All right, that is when the moles of acid are equal to the moles of base. If you're before the equivalence point, that means we have an excess of acid. That's why our pH is really low. And if we're after our equivalence point, we have an excess of strong base, which is why our pH is really high. All right, so we kind of broke this curve into these regions here. When we were calculating our pH during our titration, we had to first take our acid-base reaction that we're talking about, but in order to do our ice table, we have to convert it into moles or millimoles to keep track of how much reaction has occurred. All right, that's because we're changing the volume during our titration. So when we go back and calculate pH, we have to convert it back into molarity. All right, and that will allow us to calculate our pH. We either have an excess of strong acid, as in this case here, or an excess of strong base, as in the case of our fourth region. Cool, and then the equivalence point, again, like we just said, it's kind of the easiest one to do the pH for, but again, we also need to be able to calculate the volume required to get to that equivalence point. Cool. All right, so what we're going to do is next class period, we're going to introduce a new type of titration, starting out with instead a weak acid and a strong base. It's going to be very similar, but we know that weak acids, when they react with strong bases, depending on what is limiting, there can be a buffer that's created. So there's just going to be a little bit of a different strategy in terms of calculating our pH, but we've laid some groundwork up until now. So hopefully this doesn't look too big and scary, but looks pretty familiar. Cool. All right. We're good here. That's what we need to do for our strong acids. The weak acid, strong base titrations are a little bit more calculation heavy. But yeah, we'll go ahead and take our break now, and we'll meet back at half after for our lab.